So today we are actually using a example to show how the optimization process work and what you can do to explore the design space using optimization as a tool. And the main method we are going to use is actually by playing with the objectives and the constraints. If you remember from the last session, I think we talked about objectives and constraints briefly. If you remember the example I showed, say when you're trying to buy a laptop computer, and there are so many criteria, you can sort them based on different criteria, or you can filter them based on your preference. So those are the things actually your design criteria. If you think about design a building, you also have the qualities you're looking for. You also have a set of boundaries. Say you can only have this type of wall, not another type. Your shape will be bound within your plot, right? And also there is the concept of constraints. Say there are certain things you need to deliver, but once you reach certain level, they don't have to worry about it any further. So those are the constraints. So we'll see if we can use those things to force the optimization process into finding the right solutions you're looking for. We're going to use a tool called jEPlus+EA. There is a tutorial on how to get started with this tool. It's suitable for doing a demonstration of the optimization process. I have already uploaded a copy on Moodle. So in the and there's a video tutorial on how to get started with it. But in this tutorial, you have to download different parts of the software separately and install them. In this package, you just download the package and unzip it, and all the tools are there. But you still need to register a account. So what I did is loaded a predefined a parametric project. If you remember what parametric project is, so you have a model, you can define lots of parameters in it, and for each parameter there's a set of values you want to test, and you can also define. You can see the objectives and the constraints, and this will give you a project that optimization can work on. So I just loaded this project, and I need to do a few changes. I will call it demo 2 because I have a demo already, and this doesn't matter. And what's in this project is still using the shoebox model we have looked at several times in the past. If you remember, it's just a single box model with one external wall only and one window in that. There are a number of parameters defined for that, including the orientation of that external wall. Of the whole building, but effectively changing the orientation of that window. And the first two parameters are the heating set point and the cooling set point. The model is supposed to be located in London, so London weather is used, and we assume it needs both heating and cooling for its operation. There are other parameters included, like infiltration level or insulation or the wall construction. This varies only where the installation is located, either in the cavity or on the external side or on the internal side. The difference this makes is actually the availability of internal mass on the external wall. Because if you locate the insulation on the inside, then there's essentially no internal mass due to the external wall. Now, there is a window whose size can be varied, and there's overhang. But in this example we are going to look at, I have actually disabled all the parameters from infiltration and forward. So the window size is fixed, the wall construction is fixed, insulation level is fixed, infiltration level is fixed. All the things we are going to vary in this case are the orientation, the heating side point, and the cooling side point. This is just to make the problem simpler, so we can understand what's happening there. And if you look at the left side on this side, it gives an overview of the problem. Say if all the parameters are included, then there will be more than 100 million possible different combinations. That's quite a big number. But with only the first three, the orientation, the heating side point, and cooling side point, we have something like 3,400 different possibilities. Now, since the search space is fairly small, 3,000 is actually a tiny search space, we could actually use a full parametric run. So run all these 3,000 cases, and then you can have a look at the results and find the one you want. But of course, today's point is showing how optimization works. So supposedly with optimization, we don't even need to run 3,000. We run a few hundred, we get the results you want. So just remember, those are the three variables we have. The model will produce the annual heating consumption, cooling consumption, number of discomfort hours, and the electricity used for lighting. And they have been formulated as various objectives and constraints. The first thing we are going to try is, let's see what combination of values for orientation, heating, and cooling set points will give us the lowest heating consumption. Okay, is that question clear enough? So in order to do that, I need to actually disable all the constraints. We're not going to look at constraints in the first example. So I'll disable that. I leave the heating objective on and disable all the other objectives. Okay, so this will give us effectively only one objective. So now the problem is giving different possibilities for orientation, heating set point, and cooling set point. What should be the best combination of values of these parameters to give us the lowest annual heating consumption, right? So that's the question we are asking the optimization algorithm to answer. Okay, now let's go to the next part, and I will only need to do some small changes in here. This is a setting up the algorithm. In this tool, there's only one algorithm to choose, which is called NSGA2. Actually, in our last session, this algorithm has been mentioned. I think Yair introduced it. It's called a non-dominant sorting genetic algorithm. So this is one of the multi-objective optimization algorithms. So once you choose that, you're doing a optimization run. Because we have a very small problem, I will reduce the population size to make the thing runs a little quicker. I'll explain what the population size is later. And we only want to run it up to, say, 50 generations. We don't want to run it for too long. So that's what I need to do to set algorithm. Now, I'll name the first run as heating only, and give some note, say minimizing. And I think that's all I need to do to for setting up this run. So now I can click on the create button. This should create a project for me, and I can see the condition of the status of the project has changed to online, and we now have a start button. Now, once I click start, the optimization process will start, and it will identify some cases for me to simulate, and then this program will need to run the simulation and get results and feedback to the optimization process. So to run simulation, I use my local simulation. So I click start button. I should change the state to initializing and waiting for the simulation to be carried out. But it's not doing anything yet until I check that box. So now, okay, give it a bit more power to run it. And now you can see the simulation has been executed. So that's the first round of simulation has been done. And if you go to the next tab, you'll see the points showing up here. And each dot is actually one case. If you point to that, it will tell you, that's on the left side are the parameter values of that case. And on the right side, you can see the objective values, say heating and cooling. The process is only using heating as the objective driving the optimization process, but the other values are reported nevertheless, giving you your parameter value choices. Okay, so now we can show it in a different way. Remember, if we're only optimizing for heating, so this is actually what is going on now. So the optimization algorithm is trying to find the lowest point in terms of heating. So find a combination of parameter values that gives you the lowest heating consumption value. Okay, so both axes are heating. So the algorithm is trying to find the point that is closest to the region. If you show it on heating versus cooling, it's essentially the same, but you have to remember that the algorithm is trying to push towards that direction, so minimizing T1 only. It doesn't really care what T2 value is. And the red points are the best solutions it has found so far. And you can see there are 4 red points now, which means there are 4 different solutions which the algorithm consider to be equally good. Okay, now there are 5. The ultimate goal is actually to find all the best solutions according to your criteria. So it's populating the number of the best solutions now, and they all have the same heating value. It's 55.36 at the moment, and all of them have the same value. That's hence they were considered equally good. But now suddenly there's a new one showing up, which has a much lower heating consumption, right? And now the algorithm is using this, the new best solution, trying to figure out are there similar ones that gives the good results as well. The blue dots are the cases being simulated in the last iteration. If you have a look at here, you see every time it runs somewhere up to 6 different cases. Sometimes 3, sometimes 5, but it should never go beyond the 6, because a 6 is what we defined as the population size. Okay, so the genetic algorithm goes in iterations. So every time based on the existing solutions, it identifies a few more, and the number of cases it evaluates is defined by the population size. For more complex problems, you may need to have a higher population size, but for a very simple problem like this, 6 will be fine. I got a feeling that even 4 will do, maybe even smaller numbers. And you can see it has found another set of bad solutions already, and it's on fairly regular basis, isn't it? And they all have the same heating value, but T2, if you look at it, it's the annual cooling value. So it can have different annual cooling consumptions, but they all have the same annual heating consumption. Because we only have heating as the objective, hence the algorithm consider all of them are equally good. Okay, does it make sense? Because we're only looking at heating, and they all have the same heating value, which is the lowest comparing to the rest. So they are considered to be equally good. Okay. Now, think about the parameters we have. We have orientation. We have a heating set point, and we have a cooling set point. Those are the only 3 parameters we are considering in this case. So can you guess what are the values in those so-called optimal cases? Can anyone give me a answer? Give me a guess.
Sorry, I was messing with my sound settings just now, but can you repeat that?
Right. Sorry. I see. I got a few questions on the chat. I'll cover those in a moment. The question is, we got apparently within, say, about 200 simulations, the algorithm has already found us a set of solutions that have the lowest heating consumption, lowest annual heating consumption values. Now, considering that we have 3 variables in our project, that is orientation, heating set point, and cooling set points. So what would be your guess? The parameter values are for this case. Now, if we go back to the definition here, let's have a look at it. So the orientation, let me see, turn off this. The orientation, we are varying from, say, 0 to 360 degrees at a step of 15 degrees. So rotating the building every 15 degrees. 0 being the external wall, the windows facing south. Okay, and the heating set point is varied from 18 degree to 23 degree at 0.5 degree steps. Okay, so those are the values for the heating set point. And these are the values for the cooling set points from 24 to 30 degree at a step of 0.5 degree. So you get a range of value like that. Now, just to think about the situation, this is a single room in London, and it needs heating and cooling. And those are the three variables you can, or 3 design parameters you can use. Now, without optimization, can you think what should be your best solution if you're looking to minimize the heating consumption?
It should be south, lowest heating set point and highest cooling set point, right?
Yes, almost completely right. So do everybody agree with Peter? Okay, well, I'd say I say it's almost completely right because actually heating set points has no part in the outcome because it doesn't
Oh,
affect
okay.
how much heating consumption is. So whatever the cooling set point is, you as long as the heating set point has been set to the lowest, that is 18, and the orientation is facing due south, then you should get the lowest heating consumption. And that's because the situation is so simple, we actually don't need the optimization process to tell us the answer. But knowing that, we can actually check if the result is right. So let's look at this one. You can see P0 is I can't move my mouse. So P0 is orientation. It has a value 0, right? So that's due south, and P1 is heating set point. That has a value 18. That's the lowest heating set point we have specified in our project. And P2, which is the cooling set point, is 24 in this case. Now, if you go to the next one, it has the same annual heating consumption. And again, you see the orientation is a 0 and the heating set point is 18. That's exactly what we expect. But cooling set point has increased a bit to 25, to 24.5. If you go down to the last one, again, we see the orientation is facing south and heating set point is at the lowest, whereas the cooling set point is the highest at 30. But all these red dots are considered equally good according to the algorithm, right?
Yep.
So this already gave us some interesting insight. So it's telling you that the outcome is only dependent on the orientation and the heating set point, and no matter what the cooling set point value is, the results are the same, right? So this is what optimization. This shows how the optimization process works, and what kind of results it can give you. But of course, this is not exactly useful yet. Because we do care about cooling consumption, isn't it? So now, given the current results, how would you decide what cooling set point you want to use? Remember, we only optimized for heating consumptions. Now,
Also,
if you say, I do care about cooling consumption, and this is the results I have, which cooling set point, which we haven't really, there isn't a conclusion, say which cooling set point we should use from the results. So which one would you choose?
the highest one.
The highest one. So you want this point, right? Because at the same time of a lowest heating, it gives you the lowest cooling as well.
Yep.
No, well, okay, this statement is not very precise. So giving, so achieving the lowest cooling set point. So all these cases, all these red points achieving the same lowest heating consumption. And among those, this point give you the lowest cooling as well, right? But this one isn't a solution that gives you the lowest annual consumption considering all the possible solutions. You can see there are quite a few that actually virtually have a zero cooling consumption. if you look at T2 here, the cooling consumption is 2.44 kilowatt hour, whereas our best heating-based conclusion give you 127. Now, how do you compare this one with, say, this case, for example? Which one will you choose? This one or that one? And how?
I think we need to figure out why it's so low.
Yes, can you imagine why it's so low?
What I'm thinking is it's because it doesn't have to turn on the systems at all.
That's right.
Which is not
Nearly
ideal
all
for
the
comfort.
time you don't need to turn on the cooling system. And the reason is fairly straightforward. The cooling set point is 30 degrees, which means only the space temperature rise above 30 degrees. The cooling will be turned on. And in London, you know, this doesn't happen very often. Right? Well, in Hong Kong, it'll be probably quite still happening quite often, but in London, it's not. In a year, get a few hours. That room temperature may rise above 30 degrees. That'll be it. So when the cooling set point is very high, you don't need that much cooling. So this makes sense to me at least. So when you have a very high cooling set point, the cooling load will be very low. Right. But now the question is, you know, you can go for the lowest heating where there is still quite some cooling required. But on the other hand, there are situations where you need substantially more heating, but virtually no cooling. Now, how do you decide, you know, which one you should go to?
Is it comfort?
Not quite yet. Comfort will go there. I'll go there later. Well, you actually need to somehow combine the cooling consumption and the heating consumption. Say, for example, if both heating and cooling are provided by electricity, then can you calculate the annual electricity for cooling and heating and use that as an objective instead of cooling and heating separately? If you can, then you effectively combining these two. So an alternative would be, you know, calculating carbon emissions due to heating and cooling. Say heating is delivered by gas, and there will be a carbon factor in your gas heating system, and if cooling is delivered by electricity, then there will be a, say, carbon intensity value from the grid. Then you can, and from there you can calculate actually the combined carbon emission value between heating and cooling. That will effectively remove the confliction, say, to worry about heating and cooling separately. But still, until you have made the decision of you know, how to combine heating and cooling, it will be interesting to see how the solutions vary between heating and cooling, right? So different solutions, you know, there's one here, there's one there, you can see, but are there something in between? And maybe the best combination will be, you know, 150 for heating and 100 for cooling, and that will give you the best scenario for your design, outcome for your design. So actually, if you're interested in both heating and cooling, you would want to find a set of solutions that is going along this way, showing you the trade-off between heating and cooling, and hence give you an opportunity to choose which solution to use. And to get that set of solutions, we need to actually enable one more objective and and run the optimization again. Now we have two objectives in play, and this becomes a proper multi-objective problem. So let's see how that will give us. I just add some node to it and change. I enabled one more objective. So now both heating and cooling are enabled. I added some node, and for the algorithm settings, last time I ran to 50 iterations. This time I don't think I need that many, so I'll change it to 30, and that'll be it. Now I update project, apply changes, and then I can run this project again. Okay, it's simulating the first 6 cases. You will see the first six cases is somewhere distributed like that, and the first iteration is always random. And then it progresses, and now you can see the red dots are showing along this this front now. It's no longer showing like that. It's now the optimization process is trying to push down both heating consumption and the cooling consumption at the same time. So effectively, now we're showing on this chart heating versus cooling. So the algorithm is trying to push the solutions towards that region. So you will see a line populated along this curve here, which we normally call, which we call the Pareto front. So if you don't remember what Pareto front is, that's the optimal trade-off between your two objectives, and the solutions on there essentially means there aren't other solutions that. Okay, it's not bettered by any other solutions that is that outperforms it on both objectives. So there's no more other solutions, no other solutions. If you draw a box there, there's no other solutions within that box. So, well, you can see the algorithm is doing its trick, and it's populating this Pareto front, and hopefully find the better ones, outperforming the existing right points as well. Okay, let me have a look at other questions. Okay, while we are waiting, so Federico asked if a complex geometry possible. Yeah, not. It's a complex question to answer. In this program, in theory, yes, but the way to vary geometry, it's up to the user. So you have to provide the different geometries in the model. To vary geometry using an jEPlus model is very difficult. But if you can interface this with Rhino Grasshopper, then that'd be a good solution for that. And Simran is asking, how long does it normally take to find the best solutions? Can this be controlled? How long does it take very much depends on the complexity of the problem. Now this, the problem we are showing here is very simple. It has only 3,000 different cases. So definitely you should get your optimal solutions within, say, 300, a tenth of the search space. But that's actually not good enough if you consider the extended project, which has 100 million different cases. A tenth of the cases need to be simulated is actually no good at all. But in those cases, I think the algorithm is able to get a reasonably good set of solutions within a tiny fraction of the search space. Something like I would imagine run to something like 500 or 1,000 simulations would give you a reasonably good set of results. There's no guarantee that they will be the so-called optimal solution or the best solutions, because optimization algorithms used here, which is called a genetic algorithm, doesn't guarantee the finding of the absolute best solutions. But it'll be enough to give you a set of very good solutions that you would not be able to achieve by hand at all, using a tiny fraction of the search space. Right, so we have finished our second run, and you see the cases are populated here. And if you look at this one, that's our previous optimal heating case. So again, facing south, 18 degree for heating set points, and 30 degree for the cooling set point. So this one actually give you. But if you look at this corner here, let me zoom in a bit. That's the very best case for in terms of cooling. And this is actually facing north. So P0 is the orientation, 180 degree means rotated 180 degree. That's the window is facing north. Heating side point remain 18, and cooling side point remains 30. And it gives us the lowest cooling outcome, and the heating consumption is much higher than the other case, which we would expect. This actually, the only change between this case and the one we saw just now is the orientation. So if you flip the window around, you get the lowest cooling but highest heating. But if you let it face south, then you get the lowest heating, while highest cooling in this set of solutions. Okay, so this is our set of best solutions we got. Okay, and anywhere in between, can't move it. Well, if you look at P1 and P2, again, it's the lowest heating side point, highest cooling side point. So all of these cases have 18 for heating side point and 30 for cooling side points. All of them. I think this one may be an outlier. No, it's the same. See, all of them have 18 and 30. The only difference is the orientation. See, this one is 285 degree. That's facing, God knows, east, I think. This is southeast. See? Okay. Now, we can actually see the distribution of different parameter values. If you go to the next tab. This is a histogram of parameter values in the set of solutions we have. Now I want to change it to run. I want to look at our latest run, which is optimizing heating and cooling. And at the moment, the distribution showing all the cases. If I only show the best solutions, so only showing this set of points, then we get a distribution like that. You see P1, that's the heating set point. So all the cases having 18 degree, and all the cases, the cooling set points are 30 degree, whereas each point have a different orientation, and the different orientation give us the spread of the point. So now if you decide that say 100 kilowatt hour heating and about 100 kilowatt hour cooling is the best trade-off you want for heating and cooling, then you know this will be your solution. And you only need to orientate it to, again, this is 315. It's more or less east, isn't it? So this is this will be your the case you choose. And if you want a different trade-off at a different trade-off point, then you can pick one of those. Actually, in this tool, you can look at the drawings. There we go. Can't really tell the orientation, unfortunately. But that's so the benefit is it doesn't require you to decide how to combine heating and cooling, but instead give you a set of choices that you can decide later, and they are equally good from the optimization point of view. So does it make sense so far?
Yeah.
Okay. Let me see if there's any. Right. Okay. Now, but can you see there's a problem? Because all our design has a heating set point that's 18 and cooling set point that's 30. Can you see any problem in a realistic sense?
It doesn't make sense. Like, it's not useful because this doesn't take into account comfort.
That's right. That's exactly the case, because 30 is definitely not comfortable, and 18 for office, that'll be too cold as well. And we do have comfort value. So let's show what comfort output looks like. So this is a plotting heating comfort versus heating consumption. So the comfort metric is shown as discomfort hours. So in your simulation model, it can report the number of hours that is considered to be uncomfortable. And throughout the year, those are occupied hours. So this is an office scenario. So in total, there will be something like 3,000 hours that the space is in use. And out of those, maybe less than that, I think less than 3,000. Actually, in most cases, in all our so-called best solutions, they're highly uncomfortable, right? You want the discomfort hours to be much lower, say, I don't know, 50 hours a year or 100 hours a year to be uncomfortable. That may be acceptable, but certainly not the majority of the time. The space is not usable, right? So this actually tells you that for every design, there will be multiple criteria you need to consider. Now, and comfort is certainly one of them. Should be included in most of the practical design scenarios. And also, cost will be one of them as well, but it's not included in this project. Or maybe carbon emissions, but we'll come to carbon emissions later. So now, if you want to find the solutions that is comfortable, yet still give you, okay, I need to rephrase it. So now the problem we need to ask the optimization algorithm is actually this. What would be the lowest heating, what would be the solution that gave us the lowest heating and cooling consumption while ensuring that the environment is comfortable, right? So this is actually what we should ask, the question we should be asking. The example we have seen just now is the first one is what would be the lowest possible heating consumption, and the second one was what would be the best trade-off between heating and cooling consumptions. But actually, if we want to consider comfort level, we should ask the algorithm, say, what would be the best between what would be the best trade-off between heating and cooling while ensuring the design delivers a comfortable environment, right? So we need to add comfort in as well. Now the question is, how do you add it in? What would be your approach to consider comfort as well? If we go back to the definition of the project, we have comfort as an objective. So can we enable this objective and have that optimized with heating and cooling altogether? And okay, I tell you the answer. There are two approaches. The first one is optimize comfort along with heating and cooling. The alternative will be use comfort as a constraint, say, and within that constraint, you optimize heating and cooling. So there's a rather big difference in terms of the optimization outcome. So let's look at using comfort as an additional objective. What we need to do is to enable comfort as an objective in this project. Now we have three different objectives: heating, cooling, and comfort. And I need to change this at comfort. Heating, cooling, and comfort. And I don't need to change the algorithm settings. Now I want to update this project, apply change, go back to our scatter plot, and then start running the project again. Let me get back to heating versus cooling first. Remember our Predefined line was like that. Now, once I enabled comfort as objective, suddenly the output becomes that. Now, what's going on? Why suddenly there are so many red dots? Can you imagine? Now, the red dots are what algorithm consider to be the best solution so far. That means the algorithm suddenly believe there are hundreds of bad solutions instead of the few we saw just now. So what's going on?
I think it's like if you imagine the entire array of outcomes as like as populating a 3D space, then like the paleo front will be almost like a slice of orange peel, like close to the origin in 3D. So if you project it onto like a 2D plane that is heating and cooling, you'll get like this.
Yeah, that's that's exactly the answer. Thank you, Peter. Yes, because we are dealing with three objectives now, and the Pareto front is actually a surface. It's no longer a line. So you have to imagine this is a 2D projection of a 3D surface. And those points, although it doesn't look very good on heating and cooling, but it must be better than others on discomfort hours. As you can see in the pop out, that T3 on the right is actually 0, so that's it has no discomfort hours, and this is a limitation of this program. Obviously, we can only show 2D charts. If we show 3D, that surface would become fairly clear. But here we can only change different views. Say now we are showing cooling versus discomfort. It still looks like a mess. Now we are looking at the surface through a different angle, and it's still like that. But in any case, this should include the Pareto front. If you were all doing a two objective optimization on cooling and discomfort, so this line will be once you found all the best solutions, this line will be the same as you optimize T2 and T3. So okay. So the concept remains the same, but having a result like that is not exactly useful to agree, because as long as it's 3D, as long as it becomes a surface, there are too many solutions for you to go through in order to find the very best one you want. You can try. You can say, okay, I care more about discomfort, so I really want a solution, say, in this region with very low discomfort levels. And then within these solutions, you can try find out what the best trade-off between heating and cooling. But still, this is not straightforward. That would mean there may be a better way to formulate the project, formulate the way the optimization is run, right? Okay, so the problem is that too many objectives is not good. It has adverse impact on the performance of the algorithm as well, because that goes into how the algorithm works. I think I will skip that part for now, but let me see. Okay, because now the algorithm is pushing towards it's pushing on 3 directions. Say if it is pushing on 1, it's fairly simple. Pushing on 2, it can still manage it because it's going to the region. But suddenly it's pushing on three different directions, and there are so many good solutions, as you can see. I will have to. I basically, let me see how to explain it. So it's kind of losing its focus, because it has to, to establish a line of small number of cases is a lot simpler than establishing a full surface, right? Because in order to populate a surface, you have to go through a lot more different cases in order to make that surface fully populated. So that's definitely represent more challenge, or takes a lot more time for the algorithm to get. Okay, I think let's because we're not discussing algorithms, so let's leave it there. So just remember, if you have too many objectives, it will slow down your optimization process quite significantly. And once you got the results, it may be quite difficult to interpret because you can't easily visualize it, and there are too many cases. You have to do extra work in order to find out which are the ones you really need. So the better approach is actually reformulate your optimization project in order to get a more straightforward answer. Right now, there are two possibilities you can. There are two things you can do. The first one is the problem now is we have 3 objectives. Can you reduce it to 2 while still have discomfort as one of them? So basically,
Yeah, we
you
can
need a
have
way.
like
Yeah, go ahead.
energy consumption.
Yeah, exactly. So you can have a I actually have that there. So you can combine heating and cooling and turn it into, say, electricity consumption. If heating is from gas and cooling from electricity, you can't simply add gas to electricity because that doesn't make sense, even though they have the same unit as kilowatt hour, but still, it comes from different things. If it has come from gas and electricity, the best way is probably calculate the operational carbon emission, something like that. So this is calculating. So if it is gas heating, it divided by the efficiency of the boiler and times the carbon factor of your gas supply. So this will give you your gas consumption per kilowatt hour. So and the next part, so V2 is cooling consumption divided by the efficiency of your cooling system. Put that's constant here. That means annual COP is 3. So this gives you a electricity consumption. Plus V4 is actually lighting, but we're not looking at lighting right now. But so you could remove that. But and the electricity consumption times the carbon intensity in the grid, then that gives you the carbon, the effective equivalent carbon emission of using electricity, and then these two can be added together to calculate the carbon emission, operational carbon emission for heating and cooling and lighting in this case. So we could use a formula like that to combine heating and cooling in order to reduce the number of objectives. So what we can do is to disable this, disable that, keep discomfort, and keep the carbon emission value. So this will give us a 2 objective problem. And let me change it again. Carbon and comfort, give it an update, and start again. Now we shall see this cloud of red dots disappear in a moment. We show discomfort and go discomfort and go carbon. So T5 is carbon emission. Now again we have a new trade-off line. This is not very neat, but in any case, it's still the trade-off line between carbon emission and discomfort. So this get us back to our comfort footing, let's say. And this is a lot easier to use, as you can see. Say if you draw a line here, say I only accept solutions with discomfort hours no more than 200 hours, then your best solution is here. It's that one. So that gives you 190 hours of discomfort, but at the same time, you have the lowest carbon emission for providing heating and cooling, right? So suddenly, if you have your Predefined online with, it's actually quite easy to use, right? You only need to find which point you want to take. One is it was on the surface, then it's a bit trickier. And even worse if it is a hypersurface that you can't even you can't even visualize, can't even mentally visualize it. Okay. And if you let optimization run, it will improve on this Pareto front and maybe fill in the gap in between. But I think you see what the point is. This is by using objectives to guide your search alone. But if for comfort, actually, what we are looking for is not say absolute comfort scenarios, say absolutely no discomfort hours. This is not what we are looking for, because in reality, you just can't get everybody to feel comfortable. Whatever environmental conditions you provide, there will be some people find it uncomfortable. So that's impossible to achieve and quite pointless to do as well, because even if you can find one, you find the cost will be too high. So the more realistic scenario is actually you draw a line here, say anything with discomfort hours under 200 will make me happy. And in that sense, you are saying that anything under 200 for discomfort hours you consider are equally valid or equally good. Okay, so if you have a criteria that you can formulate in this way, that is essentially a constraint, because you're saying that everything between 0 and 200 are okay, everything beyond 200 are not okay. That's what you're saying. And if there's a constraint, then having discomfort as a constraint will actually make the solution a lot cleaner. And we can have a look at how that works. So let's go back to our project settings, and we disable the carbon emission. We go back to heating and cooling, actually, and we remove discomfort, and we remove it as a objective, but enable it as a constraint here. So this is our constraint discomfort limit as a constraint. And when you're defining a constraint, you need to define the a feasibility range. So within so what value you consider as acceptable and what is not. So that is in this program, it is defined as the lower bound and the upper bound of that value. For discomfort, this is the number of hours. So the lower bound will be 0, and upper bound, the maximum number of discomfort hours we can accept, we'll put it 200 there. And the max value, this is a trick for scaling the output. This is something related to the algorithm. You just need to give it, you just need this value to cover the full range of the possible outcome. So for discomfort, it's going up to something like 2600. So we put 3000 there, will be enough. So, but the important value here is actually 200. So that would mean anything between 0 and 200 will accept it as a good result. So that's your constraint. Now we have one discomfort as the constraint, and we have heating and cooling as the objectives in this new setup. So I need to change this again. I call it heating versus cooling, giving the constraint comfort as a constraint. So minimizing cooling constrained by comfort. Okay, so this is our latest formulation of the optimization project. Now we update it again. apply changes and start running. And let's see how this chart will change now. Right. We suddenly got a lot of gray dots. Those are the infeasible solutions, which means it's not meeting our criteria for discomfort hours. You can see on the right side towards the bottom, that's S3 is the discomfort limit. This case has a value of 300, which is above our threshold. So 200 is here. Say everything on the left of 200 is white with a red edge. So those are the feasible solutions, or the solutions we are accepting, and the rest are the infeasible ones. So let me change it back to the heating and cooling view. You can see the Pareto front will change its shape. It used to be here, right? When we don't have that constraints, they're highly uncomfortable, but fairly low on energy consumption. But now once we draw a line on comfort, the Pareto front will likely to be somewhere here. Okay, it certainly moved further away from the region, but that gives us a more practical solutions. And if you leave it run for a little while, that trade-off line, that new Pareto front will form, and then you can pick a solution from there and say, okay, I know this is the best solution energy-wise, where we are guaranteed to deliver the comfort level that we need. Okay. So I'll leave it running for a little while. It shouldn't take too long. And okay, let me see. Minimize discomfort. Okay. Sorry, I'm not keeping an eye on chat. So what do V2? Okay, in the formula. So V1, V2 is it's the values reported by simulation, and those are the input value that you can use to calculate your the constraints and objective functions. So V1 to V4 are defined here, and it's defined in the models. And there is there are tutorial on the on Moodle to take you through, say, from Design Builder to EnergyPlus to jEPlus and then jEPlus+EA. So it takes some time to set to go through this this learning curve, but this tool has its advantage. You can do optimization in Design Builder, but it's not easy to change objective, change constraints, and and look at your solutions in a flexible way, like this tool. Although the algorithm is exactly the same. Actually, Design Builder's algorithm for optimization is it's the same code base as this tool here. So Okay, so I think, well, we only run it for 30 generations. So far we have simulated nearly 700 cases. So after so many different experiments, let's say. So it's fairly efficient. Optimization process is very efficient. And if you do want to run this project, I suppose you can enable all the other parameters. And to do that, you just need to remove this filter in the subdomain, and this will let you have all the parameter values, all the design options that you have in the project, and give you the full 100 million different possibilities. And for that, we can actually run now, call it full. With a full search space, and in this case, I'll need a bit more, a larger population size, I think. Give it 20, and let it run a bit longer. And I think that'll be it. Change it to 12, update. Apply changes and start it again. We'll see a lot more points popping up, and you will see the with other design parameters, we'll expect the Pareto front can be improved quite significantly. So let's see if it works or not. Well, you can see already there's a visible point found here. It was somewhere there, isn't it? So you can see with other design options included, the best solution will move quite a bit further.